An interstellar object is passing unusually close to Earth, and it's not behaving the way a normal comet should. Known as 3I Atlas, it is shifted in color from green to a metallic gold, a change that suggests something fundamental is happening on its surface. It shows signs of abnormal acceleration, a rare anti-tail pointing toward the Sun, and motion that appears more directed than expected. These details have led some scientists to ask an uncomfortable question: are we looking at a natural visitor or something engineered? In this episode, we examine the observations, the physics behind them, and what they truly imply. If you appreciate careful science over speculation, like the video and subscribe. Let's begin. On December 15th, 2025, observations from multiple observatories converge on a single object moving quietly through the inner region of the solar system. The object is known as 3I Atlas, an interstellar comet that did not originate around our Sun. Its current position places it closer to Earth than at any previous point in its observed passage. This proximity alone does not imply danger, but it does mean that measurements are now more precise, more frequent, and more revealing than before. As a result, attention has shifted away from where the object is going and toward how it is behaving. In planetary science, the word dangerous has a specific meaning. It does not refer to appearance or unfamiliarity, but to trajectory, velocity, and physical response to heat and radiation. Objects that pose a risk tend to show unstable motion, rapid fragmentation, or unpredictable changes in direction when exposed to a star's energy. 3I Atlas does not fit this pattern. Its orbit remains well constrained, and there is no indication of an imminent collision. The concern is not impact, but interpretation. The question scientists are now asking is whether its behavior follows the rules normally used to describe comets. With continued observation, new data have been released by several research groups, including imagery and spectral measurements. These updates have drawn attention because they show a clear shift compared to data recorded only days earlier. The change is not subtle. It is consistent across instruments, wavelengths, and observing locations. When independent measurements align this closely, the signal is considered reliable. What they show is that the coma, the cloud of materials surrounding the nucleus, has changed its optical character. For weeks, the glow around 3I Atlas carried a faint green tint. This color is familiar to astronomers. It commonly appears when diatomic carbon molecules are released from a comet's surface and excited by sunlight. These molecules emit light at specific wavelengths, producing the greenish hue often associated with active comets approaching a star for the first time. It is a sign of volatile material rapidly sublimating, turning directly from ice into gas. That behavior was expected. What is now observed is different. The green emission has faded, replaced by a soft golden tone. This color does not come from glowing gas, but from sunlight reflecting off solid particles. The shift suggests that gas production has slowed, while dust has become the dominant component of the coma. Visually, the outline appears smoother and more uniform. Scientifically, this indicates a change in the physical process occurring at the surface. Sublimation is not a single event. It evolves over time. Early in a comet's approach, volatile ices erupt unevenly, creating jets and plumes. As those materials are depleted, heavier compounds remain. These release more slowly and do not produce sharp outbursts. The surface becomes less active, not because energy has decreased, but because the most reactive materials are gone. This process is known as cometary aging. In aging comets, dust begins to linger near the nucleus instead of being pushed away by strong gas flows. The surrounding cloud grows denser and calmer. Instead of chaotic structures, the coma takes on a more rounded and stable shape. For an object that may have traveled between stars for millions of years, this effect would be amplified. Radiation, cosmic particles, and repeated heating cycles gradually erode fragile features, leaving behind a compact and resilient core. What stands out is how restrained this evolution appears to be. 3I Atlas is not showing sudden flares or fragments breaking free. There are no violent jets changing its spin or path. Its motion remains smooth. It appears to be gliding rather than reacting. This behavior contrasts strongly with comets native to our solar system. When those objects reach similar distances from the Sun, they often crack, hiss, and shed material in unpredictable directions. Their paths wobble slightly as jets act like uneven thrusters. The golden coloration supports this difference. It points to a surface dominated by dust and complex organic compounds rather than exposed ice. One possibility is a thick layer of tholins. Tholins are carbon-based materials formed when simple molecules are altered by radiation over long periods of time. They are dark, durable, and resistant to heat. In interstellar space, where exposure lasts far longer than within a planetary system, such a layer could become especially tough. Spectral analysis helps clarify this picture. When scientists examine the light from 3I Atlas split into its component wavelengths, certain signals stand out. The emission associated with carbon gas has dropped sharply. At the same time, reflected sunlight has increased. This reflection comes from dust grains, and their properties matter. The data show that these grains are remarkably uniform in size, measured on the scale of microns, which means millionths of a meter. In natural systems, size distributions are usually broad. Collisions, erosion, and turbulence tend to produce a wide range of particle sizes. Uniformity is uncommon. When it appears, it suggests either a sorting process that strongly favors a narrow range, or a surface that releases material in a controlled way. At present, there is no definitive explanation. The prevailing view remains that 3I Atlas is a natural object. Still, the measurements are pressing against the edges of existing models. Stability is the recurring theme. The object maintains its structure, sheds heat gradually, and responds to solar radiation without disruption. From an engineering perspective, these are desirable traits for any probe designed to endure long journeys. That comparison does not imply design. It highlights how unusual it is for natural bodies to display this level of endurance under stress. The physics allows it, but rarely delivers it so cleanly. The environment 3I Atlas has crossed is among the harshest known. Between stars, temperatures fall to near absolute zero, meaning nearly 0 degrees above the lowest possible temperature. At the same time, high-energy particles continuously strike exposed surfaces. Over time, weak materials are stripped away. What remains is compact, dense, and polished. As the object now warms in sunlight, it does not disintegrate. It responds slowly, as if the outer layers have already been conditioned for this transition. This polishing effect is similar to what happens to a stone carried by a river for many years. Sharp edges are worn down. The shape becomes smooth. In this case, the smoothing occurs through radiation and time rather than water. The result is a surface that reflects light more efficiently than expected. This property is known as albedo, a measure of how much light a surface reflects rather than absorbs. Typical comets have very low albedo. They appear dark, almost black, because their surfaces absorb most incoming light. 3I Atlas reflects more, not like a mirror, but enough to change its apparent color. When sunlight interacts with a moderately reflective, dust-rich surface, the scattered light takes on a warm, golden tone. That reflectivity, combined with the fading of gas emissions, explains the transformation now observed and marks the final point of this sequence of observations. To understand what is unfolding, it is necessary to look beyond the solar system and consider the environment this object may have come from. 3I Atlas did not form around our Sun. Its origin lies in another stellar system, possibly one very different from our own. Stars vary widely in size, temperature, and radiation output. A red dwarf star, for example, is smaller and cooler than the Sun, but it produces intense magnetic activity and frequent flares. A massive O-type star, on the other hand, is extremely hot, short-lived, and floods its surroundings with high-energy ultraviolet radiation. Material forming around such stars experiences chemical pathways that simply do not occur in our local neighborhood. If 3I Atlas originated in one of these environments, its composition would reflect that history. The ices locked into its structure could include substances that are rare or unstable near the Sun. When such ices begin to warm, they do not behave like ordinary water ice or carbon dioxide ice. Their sublimation thresholds are different. Their byproducts interact with light in unfamiliar ways. This makes the recent shift from green to gold especially important. It may represent the signature of a specific class of exotic ice transitioning from solid to gas, mixed with complex organic material that does not fluoresce in the same way as diatomic carbon. One candidate often discussed is nitrogen ice. Nitrogen ice sublimates at much lower temperatures than water ice and can remain stable only in extremely cold environments. When it does begin to sublimate, it can do so smoothly, without explosive jets. If nitrogen ice is mixed with heavy organic compounds, the gas production may be modest, while dust remains dominant. This combination would naturally suppress bright gas emissions and enhance reflected sunlight, producing the muted golden appearance now observed. While this explanation remains hypothetical, it is grounded in known physics and laboratory measurements of cryogenic materials. There is another detail that sharpens this picture. The timing of the color change is not random. It occurred almost exactly as 3I Atlas crossed the orbital distance of Mars. For humans, that boundary is arbitrary, defined by planetary paths. For solar physics, it marks a meaningful transition. Beyond the orbit of Mars, the intensity of solar radiation pressure and the density of the solar wind increase noticeably. Charged particles from the Sun become more influential, and the balance between gravity and radiation forces begins to shift. A typical natural object responds passively to this environment. As solar radiation pressure increases, gas in the coma expands outward. Light particles are pushed away more strongly than heavy ones. The result is a broader, more diffuse cloud and a tail that grows longer and more chaotic. Heating accelerates sublimation, and the object becomes less stable, not more. This pattern has been observed repeatedly in comets native to the solar system. 3I Atlas is not following that script. As it entered this region, its coma did not balloon outward. Instead, it tightened. The cloud of materials surrounding the nucleus appeared to streamline itself, drawing closer to the body rather than dispersing. This behavior is difficult to reconcile with purely ballistic expectations. The object seems to be interacting with the solar wind in a way that minimizes drag instead of maximizing it. Time-lapse imagery provides one of the clearest views of this process. Observations taken over a 12-hour window show the coma maintaining a consistent shape, rather than expanding evenly in all directions. The material sweeps back and hugs the nucleus. The outline remains stable from frame to frame. This is not a brief fluctuation. It is a sustained configuration. In everyday terms, the shape looks aerodynamic. In the vacuum of space, traditional aerodynamics do not apply because there is no air. However, solar dynamics do. The Sun emits a constant stream of particles and photons. These exert pressure, especially on small, lightweight material. The way an object presents itself to that flow determines how much force it experiences. A broad, gas-rich coma catches more of that pressure. A compact, dust-dominated coma catches less. By maintaining a tight coma, composed primarily of heavier particles, 3I Atlas effectively reduces the push it receives from the Sun. This allows it to maintain its trajectory with unusual precision. For experts who model orbital dynamics, this level of stability is surprising. Small, natural bodies typically show subtle but measurable deviations when non-gravitational forces come into play. Here, those deviations are minimal. Attention then turns from shape to light itself. Spectroscopic measurements from the Keck Observatory in Hawaii have revealed another unexpected feature. The light reflecting off the coma shows a measurable degree of polarization. Polarization occurs when light waves oscillate preferentially in a particular direction. A familiar example is sunlight reflecting off a calm lake, which becomes polarized and can be reduced with polarized sunglasses. In cosmic environments, polarization carries information about surfaces and particles. Randomly oriented dust grains tend to scramble light, producing weak or inconsistent polarization. When dust grains are aligned, the reflected light shows a clearer, more structured polarization signal. The readings from 3I Atlas indicate that the dust in its coma is not tumbling chaotically. The particles appear to share a preferred orientation. This raises a series of questions. Dust alignment can occur under certain conditions. Strong magnetic fields can cause elongated particles to line up. Rotation of the nucleus can impose order on material released from the surface. Another possibility is that the dust itself has magnetic properties, allowing it to respond directly to external fields. Each of these explanations carries significant implications. If the dust is magnetic, the object as a whole could interact with the sun's magnetic field in a more complex way than previously assumed. The sun's magnetic field extends far into space, carried outward by the solar wind. An object with a charged or magnetized surface moving through that field would experience a force known as the Lorentz force. This force acts perpendicular to both the direction of motion and the magnetic field. The key point is that such an interaction does not require engines or expelled propellant. It arises naturally from the laws of electromagnetism. Under the right conditions, it can alter an object's trajectory, subtly but continuously. This does not mean that 3I Atlas is deliberately steering. It means that the physics allows for controlled interaction with the environment if certain properties are present. The golden shift in appearance may be the first visible indicator that 3I Atlas is not merely a passive rock responding to gravity alone. It appears to function as a system, one whose surface composition, dust behavior, and interaction with solar forces are tightly coupled. Each observation by itself can be explained within natural frameworks. Taken together, they form a pattern that is difficult to ignore. What is especially striking is the contrast between the object's calm exterior and the complexity of the processes shaping it. From the front, illuminated by sunlight, the coma looks smooth and restrained. There are no violent outbursts, no chaotic sprays of gas. Everything appears quiet, almost serene. But this calm is deceptive, because while the light in front of the object is changing in subtle ways, something else is happening behind it. In the region of shadow trailing the nucleus, astronomers have detected a structure that does not fit the simple geometry of a comet moving toward the sun. A feature is emerging where none should exist. This structure is oriented in the wrong direction. Instead of pointing away from the sun, as a normal dust tail would, it points inward, toward the sun, and it is growing. This phenomenon is known as an anti-tail. Anti-tails are rare and typically appear only under very specific viewing conditions. In this case, the geometry alone does not fully account for what is being observed. The emergence of the anti-tail coincides with the color shift and the tightening of the coma. The timing links these changes together. The same transition that produced the golden halo appears to be associated with the formation of this backward-pointing structure. This connection suggests that the processes shaping the coma are also shaping the tail, and that both are responding to forces not fully captured by standard comet models. The picture that emerges from these observations is remarkably consistent. A quiet, golden halo moves steadily through space, holding its course with unusual precision. Trailing behind it is a structure that does not align with expectations. Becoming more defined as measurements improve, this anti-tail is not simply a visual oddity. Its orientation, growth, and timing place it in direct tension with standard models of comet behavior. When these features are considered together, it becomes clear that 3I Atlas is no longer just slightly inconsistent with conventional explanations. Its behavior now challenges them in a more fundamental way. The earlier shift from green emission to a golden, reflective glow pointed to an unexpectedly restrained surface and activity pattern. What has followed is more difficult to reconcile. Attention moves naturally away from the coma itself and toward the structure trailing the object, because it is there that the strongest conflict with existing models appears. At nearly the same time, the optical properties of the coma changed. Observational data collected around December 14th and 15th confirmed the development of an anti-tail. An anti-tail is a real, documented phenomenon in comet science, but it is also one that is often misunderstood. In most cases, it is not a physical tail pushing material toward the sun. Instead, it is a geometric effect. When Earth passes through or near the plane of a comet's orbit, heavier dust that lags behind the nucleus can appear. From our perspective, to point sunward, the dust is still following the comet's orbital path. Only the viewing angle changes. In such cases, the behavior of the anti-tail is entirely predictable. Its apparent orientation depends on the relative positions of Earth, the comet, and the Sun. As Earth moves, the angle shifts smoothly and gradually. There are no abrupt changes, no sharp pivots, and no independent motion. Once the geometry changes again, the anti-tail fades or reorients accordingly. This pattern has been observed many times, documented, modeled, and largely understood. What is being observed with 3I Atlas does not follow this pattern. New imagery and telemetry indicate that the anti-tail associated with this object is not behaving as a passive projection. Its orientation has changed relative to the nucleus itself, not merely relative to Earth, over a span of roughly 12 hours. The angle between the anti-tail and the main body shifted by approximately 3 degrees. In interplanetary space, this is not a trivial adjustment. It is far larger and faster than what would be expected from a simple change in perspective. An optical illusion cannot do this. A perspective effect depends entirely on the observer's motion. It evolves continuously and predictably. It does not change direction independently of that motion. The data indicate that the structure itself is dynamic. Material within the anti-tail is responding to forces that alter its direction in real time. This places it outside the category of a standard dust trail illusion. Under normal conditions, when a comet releases dust, the dust inherits the comet's orbital momentum. Once released, the particles spread out along the orbit. Radiation pressure can push smaller grains away from the sun, but it does so gradually. The dust does not suddenly veer off at sharp angles. It does not execute rapid directional changes. In short, it does not behave as if it has agency. The observed 3-degree shift over half a day implies an active process. The question then becomes, What kind of process could produce such behavior? From a physics standpoint, there are two broad possibilities. The first is a violent, directed outburst. In this scenario, a pocket of volatile material beneath the surface ruptures, releasing gas and dust in a focused jet. This is known as a non-gravitational acceleration event. Such events are well documented. They can act like thrusters, briefly altering a comet's velocity. If this were the case, 3I Atlas would be venting gas forward toward the Sun, producing a transient structure that might resemble an anti-tail. However, this explanation carries consequences. A powerful, asymmetric outburst would impart torque. The nucleus should begin tumbling. Its rotation state should change. Its light curve, which tracks brightness variations over time, should become irregular as different surfaces rotate into view. This is not what the data show. The light curve of 3I Atlas remains remarkably flat. Brightness variations are minimal and consistent. This indicates a stable rotation state. There is no evidence of chaotic spinning or rapid reorientation. The object appears dynamically calm, even as the anti-tail evolves. The second possibility is that the observed structure is the result of a sustained, stable reactive force instead of a brief explosion. This would involve a controlled release of material or energy applied in a consistent direction. For such a force not to induce tumbling, it would need to act very close to the object's center of mass. From the standpoint of classical mechanics, this is a stringent requirement. Forces applied off-center generate rotation. Avoiding that outcome requires either precise symmetry or deliberate alignment. Within purely natural frameworks, achieving this level of precision is difficult. It is not impossible, but it is rare. The physics does not forbid it, but it does not favor it either. This is why the behavior has drawn attention. The anti-tail does not look like the byproduct of a messy, random process. It looks organized. Velocity data deepen this concern. A recently released dataset tracks the object's velocity vector with high precision. Under gravity alone, an object falling toward the Sun accelerates in a well-defined way. The equations governing this motion are straightforward and have been tested extensively. 3I Atlas deviates slightly from this expectation. Its speed is marginally higher than predicted. The difference is small, on the order of a fraction of a percent. In everyday terms, that sounds negligible. In orbital mechanics, it is not. Over astronomical distances, such a discrepancy accumulates rapidly. A fractional change in velocity can determine whether an object passes safely by a planet or intersects its orbit by millions of miles. Precision matters. What is notable is that this excess speed appears at the same time as the anti-tail becomes prominent. The correlation does not prove causation, but it is difficult to ignore. If a force is acting to alter the object's motion, the anti-tail could be a visible manifestation of that interaction. In spaceflight, trajectory adjustments are made by firing thrusters in specific directions. Applying force along the direction of motion increases speed. Applying it against the direction of motion decreases speed. Applying force perpendicular to the direction of motion alters the path without significantly changing speed. The orientation of the anti-tail, relative to 3i Atlas and the Sun, places it close to this perpendicular configuration. From a purely geometric standpoint, the alignment is consistent with a steering correction rather than a braking or acceleration maneuver. This does not imply intent. It describes a physical similarity. The laws of motion are indifferent to purpose. They only describe outcomes. At this stage, the discussion remains firmly within physics. The steering hypothesis is controversial precisely because it sits at the boundary between rare natural behavior and behavior more commonly associated with engineered systems. What strengthens the case for taking it seriously is not speculation, but consistency. The object is not tumbling. Its brightness remains stable. The applied force, whatever its origin, appears to be balanced. The issue of balance brings the center of mass into focus. For an object to experience sustained force without rotation, the net force must pass through its center of mass. In irregular natural bodies, this alignment is unlikely. Internal structures are uneven. Outgassing vents are asymmetrically distributed. As a result, natural jets tend to spin objects up or down. Engineering solves this problem by design. Thrusters are placed to produce desired motion without unwanted rotation. Again, this does not assert that 3i Atlas is engineered. It highlights why the observed stability is difficult to reproduce accidentally. Composition adds another layer. Spectral readings show that the main tail of 3i Atlas is consistent with expectations. It contains dust and water ice, cold and relatively inert. The anti-tail, however, shows a different signature. It is richer in ionized particles. Ionization occurs when atoms or molecules lose electrons, typically due to high energy input. Ionized material interacts strongly with magnetic fields and emits differently than neutral dust. This implies that the anti-tail is energetically distinct from the main tail. It is hotter. It is more reactive. It resembles a flow of energized particles rather than a passive trail of debris. In cometary science, this kind of distinction is unusual. Tails typically differ by particle size and charge state, but not in a way that suggests separate mechanisms operating simultaneously. This combination of features inevitably invites comparison to the first known interstellar object detected in 2017. Often referred to as Oumuamua, that object also exhibited non-gravitational acceleration. It also defied expectations. It showed no visible tail, yet it changed speed. Various natural explanations were proposed, including outgassing of hydrogen or nitrogen ice. None fully resolved all observations. 3i Atlas presents a different configuration. It does have a tail, but the most prominent and dynamic component is oriented incorrectly by conventional standards. It is as if the object resembles a comet in broad outline but diverges in critical details. The behavior is close enough to familiar patterns to invite classification, yet different enough to resist it. This resemblance without full conformity has been described as a form of imperfect camouflage. The object fits just well enough within existing categories to be observed and tracked using known methods. At the same time, its deviations accumulate. Color, stability, velocity, polarization, and now tail geometry all point to a system that does not behave like an ordinary fragment of primordial debris. Taken together, these features place increasing strain on the natural object framework, not by disproving it outright, but by revealing gaps in how the object's motion and energy exchange are currently explained. One of those gaps appears most clearly in the object's trajectory. If the changes in motion inferred from recent data reflect an additional force acting on 3I Atlas, then the immediate question is not whether it exists, but what effect it has. Orbital modeling indicates that without this influence, the object would have passed through the inner solar system at a greater distance. It would still have been detected, but with reduced observational quality. Radar returns would have been weaker, spectral resolution lower, and fine structure in the coma and tail more difficult to resolve. The adjusted path does not imply danger. There is no indication of risk to Earth. Instead, it brings the object into a region where observation is unusually favorable. In planetary science, there exists an informal concept, sometimes described as an observational sweet spot. At certain distances, objects are close enough for detailed study, but far enough to avoid saturation, interference, or dynamic instability. 3I Atlas is now passing through such a zone. It is close enough for high-precision tracking and detailed spectroscopy, yet distant enough that its motion remains smooth and predictable. This balance is rare. It is also striking that the inferred correction aligns with it so closely. This does not imply intent. It establishes consequence. The result of the altered trajectory is improved visibility across multiple instruments and methods. The object is now accessible to radar systems, optical telescopes, infrared sensors, and polarization studies at levels that would not have been possible along its original path. From a scientific standpoint, this transforms the encounter. Instead of a fleeting detection, it becomes a prolonged observational event. This distinction matters. A passive rock moving under gravity alone is a static subject. It can be catalogued, measured, and classified. What is unfolding here is different. The sequence of changes, color shift, coma restructuring, anti-tail development, velocity deviation, suggests an evolving interaction with the solar environment. The object is not merely present, it is responding. That response is what has drawn the sustained attention of researchers across multiple disciplines. As the data have accumulated, interest has expanded beyond orbital dynamics and comet chemistry. Some researchers have begun to ask whether the assumptions framing the analysis are still sufficient. Among the most visible voices in this discussion is Harvard astronomer Avi Loeb. His involvement is not new. He was among the first to argue that the anomalous acceleration of the interstellar object detected in 2017 warranted consideration of artificial origins. That position placed him outside the mainstream consensus, but it also ensured that the possibility would not be ignored. In the case of 3I Atlas, Loeb has reiterated a simple logical premise. Humanity has already demonstrated the capacity to send technological objects beyond its home planet. Probes such as Voyager, Pioneer, and New Horizons were designed to leave the solar system entirely. Voyager carries a golden record, an intentional artifact meant to outlast its creators. These missions were launched not by a global government, but by a single species at an early stage of technological development. The act of sending durable objects into interstellar space is therefore not hypothetical. It is established fact. Given enough time, such objects can drift between stars. If one civilization can do this, others could as well. This does not require advanced propulsion beyond known physics. It requires patience, material resilience, and a willingness to launch something that may not be encountered for millennia. Loeb has suggested that 3I Atlas could represent the result of such a process, not as part of a coordinated exploration program, but as a byproduct of private or non-state activity. In human terms, not every spacecraft is a flagship mission. Some are test platforms. Some are demonstrations. Some are symbolic. The solar system already contains debris from past launches, defunct satellites, and spent stages. On longer timescales, this accumulation becomes substantial. Extending this logic outward, interstellar space may not be pristine. Over millions of years, technological civilizations could seed their surroundings with artifacts, some intentional, some incidental. These objects would not announce themselves. They would drift. Most would remain undetected. Only those with unusual surface properties, favorable trajectories, or reflective characteristics would stand out against the cosmic background. This perspective reframes the encounter. Instead of asking whether 3I Atlas represents first contact, the more appropriate question becomes whether it represents detection. Detection does not imply communication. It implies recognition. A relic does not speak. It persists. Trajectory backtracking adds weight to this view. When astronomers project the object's path backward using current velocity data and reasonable assumptions about past interactions, the result suggests that 3I Atlas entered the outer regions of the solar system thousands of years ago. Estimates cluster around a timescale of roughly 8,000 years. The uncertainty is significant, but the order of magnitude is consistent across models. 8,000 years is a long time in human terms. When this object crossed the heliopause, the boundary where the solar wind yields to interstellar space, human societies were in early stages of agriculture. Writing had not yet emerged. Monumental architecture lay far in the future. For the entirety of recorded history, 3I Atlas would have been moving slowly inward, passing through the Oort cloud. The Oort cloud is a vast, diffuse shell of icy bodies surrounding the solar system, extending far beyond the orbit of the outer planets. It is cold, dark, and sparsely populated. Objects move through it at low relative speeds. An interstellar body entering this region would experience minimal disturbance over thousands of years. Gradual gravitational interactions would guide it inward. The slow pace of this journey is sometimes cited as an argument against artificial origin. Advanced technology is often associated with speed. This association is misleading. High velocity is not always desirable. A probe designed to survey a system, collect data, or persist over long durations would benefit from stability and low energy expenditure. Moving slowly reduces thermal stress. It simplifies navigation. It extends operational lifespan. In this context, gradual approach is not a limitation. It is a feature. A slow-moving object can remain intact for millions of years. It can passively monitor its environment. It can respond only when external conditions change, such as increased solar radiation. This brings attention back to composition. Spectral analysis indicates that 3I Atlas contains significant amounts of carbon dioxide, water, ice, and simple organic compounds. These materials are common in comets, but their relative abundance and behavior here are notable. Carbon dioxide and water are fundamental to terrestrial life. Organic molecules form the basis of complex chemistry. Together, they represent a minimal toolkit for biological processes. One speculative interpretation is that such composition aligns with what might be expected from a life-seeding mechanism. This idea is known as directed panspermia. Unlike natural panspermia, where life spreads through accidental transfer on meteoroids, directed panspermia involves intentional distribution of biological precursors. The concept does not require advanced life to survive the journey. It requires only that the building blocks be delivered intact. Within this framework, a durable object coated in protective material and carrying frozen volatiles could drift between systems, releasing material when conditions become favorable. The observed golden surface could function as a shield, protecting internal contents from radiation. The apparent braking behavior associated with the anti-tail could reduce entry velocity, preventing destructive heating. This interpretation contrasts with another possibility, often described as an observational or entrepreneurial scenario. In this case, the object would function primarily as a sensor platform. As it approaches a star, increasing solar energy would activate systems that had remained dormant. Solar radiation provides a reliable power source. A probe relying on it could remain inactive for long periods, conserving internal resources. Under this scenario, the recent changes in appearance would correspond to activation rather than decay. The tightening coma, increased reflectivity, and energetic tail could reflect systems coming online. The object would not need to transmit signals immediately. It could record, store, and continue on its path. These two interpretations differ in emphasis, but they share a critical point. Both rely on known physical principles. Neither requires speculative propulsion or exotic matter. Both depend on time, scale, and durability rather than speed or force. At this stage, it is important to emphasize what the data do and do not show. There is no direct evidence of communication. There are no confirmed transmissions. There are no encoded signals in the light observed so far. All conclusions remain constrained by physical measurements of motion, composition, and interaction with solar forces. What has changed is the scope of inquiry. Telescopes alone are no longer sufficient to address the full range of possibilities. Optical and infrared observations describe surfaces and temperatures. Spectroscopy reveals composition. Orbital analysis constrains motion. Together, they describe a physical object behaving in unexpected ways. If additional layers exist, they may not be visible in reflected light. They may instead appear in patterns of emission outside the optical spectrum, in radio frequencies, or in subtle modulations that resemble background noise unless deliberately isolated. At this stage, the investigation presses against the limits of what light alone can reveal. The object is no longer examined solely as something illuminated by the sun, but as a system whose behavior may leave signatures in other forms of energy. That possibility places radio observation at the center of attention. Large dish arrays across the globe have been directed toward 3i Atlas, not to image it, but to listen. This shift matters because comets are typically quiet at radio frequencies. When emissions do occur, they are weak and irregular, generated by charged particles in the coma interacting with the solar wind. The result is usually broadband noise with no internal structure, drifting and fading in patterns consistent with turbulent plasma rather than any organized source. The radio emissions associated with 3i Atlas do not fit this description cleanly. Measurements taken over the past day show fluctuations that are not consistent with random noise from an irregular, tumbling body. Instead of drifting unpredictably, parts of the signal repeat. Certain features recur at regular intervals. This does not automatically imply intent or design, but it does place the signal outside the simplest natural category. The boundary between natural emission and structured signal is thinner than many assume, and this is where interpretation becomes difficult. In radio astronomy, identifying structure requires extreme caution. Human perception is well known for finding patterns where none exist. This tendency, called pattern recognition bias, has complicated signal searches for decades. Early SETI experiments produced many false alarms caused by satellites, terrestrial interference, or coincidental alignment of noise. As a result, the default scientific posture is skepticism. Any apparent structure is assumed to be natural or instrumental until proven otherwise. With that context in mind, analysts began examining the telemetry from 3i Atlas using standard signal processing techniques. They filtered out known sources of interference and corrected for instrument response. What remained still showed internal order. Certain mathematical relationships appeared repeatedly within the modulation of the signal. These relationships are what have drawn attention, not because they resemble messages, but because they resemble known mathematical forms that rarely arise by chance in radio emissions from small natural bodies. Some analysts noted that portions of the modulation resemble the paired, helical structure often used as an analogy for deoxyribonucleic acid, commonly known as DNA. This comparison does not refer to biological material or genetic code. It refers strictly to geometry. The radio signal appears to oscillate in two linked frequency components that rise and fall together in a regular, intertwined pattern. In signal terms, this is known as paired helical modulation. To understand why this matters, it helps to consider how radio signals are generated. Natural sources tend to produce either single-frequency emissions or broad, noisy spectra. Complex modulation usually requires a stable, rotating system or multiple emitters acting in precise synchronization. In engineered systems, this is achieved deliberately. In natural systems, it is uncommon, especially in small, irregular objects like comets. Producing two synchronized oscillations that maintain phase alignment over extended periods is not impossible, but it is statistically unlikely without a stabilizing mechanism. A second mathematical feature has also been identified. Parts of the signal show a twisting pattern in polarization that mirrors equations used to describe the space-time geometry around a rotating black hole. Known in physics as a Kerr black hole, this does not mean the signal originates from a black hole or encodes astrophysical imagery. It means the polarization rotates in a way that follows a specific mathematical curve associated with frame dragging, a relativistic effect predicted and confirmed in other contexts. Polarization describes the orientation of a wave's oscillation as it travels through space. In many natural radio sources, polarization changes erratically due to turbulence and magnetic fields. The polarization behavior observed here is smoother and more coherent. It follows a consistent rotational pattern over time. Finding this level of mathematical regularity in the radio emission of a comet-like object is unusual. Though not formally impossible, these observations have prompted discussion about whether certain mathematical structures could function as universal reference points. Mathematics does not depend on language, culture, or biology. Physical constants, geometric relationships, and fundamental equations are the same everywhere in the universe. For this reason, SETI researchers have long argued that if a civilization attempted to create a recognizable signal, it would rely on such universals rather than arbitrary symbols. Historically, SETI searches have focused on simple markers, such as narrowband signals or sequences of prime numbers. The reasoning is straightforward. Natural processes rarely generate such patterns. While technological systems can, the features observed in the radio emissions of 3I Atlas do not match classic SETI beacons, but they do intersect with this broader idea. They appear structured without being simple, ordered without being overtly repetitive. At the same time, alternative explanations remain viable. One proposed mechanism involves beat frequencies. If the nucleus of 3I Atlas rotates while interacting unevenly with the solar wind, it could periodically modulate radio emissions. As charged regions rotate in and out of alignment with external fields, they could produce rhythmic pulses. Beat frequencies arise naturally when two similar oscillations interact, creating a third pattern that appears ordered even though it is emergent. Another explanation centers on plasma physics. The interaction between a magnetized object and ionized particles in its own tail could produce polarization effects. Twisting magnetic field lines can rotate the polarization of emitted radio waves. In this view, the mathematical resemblance to known equations is coincidental. The same equations describe many physical systems. Similar math does not imply shared origin, even among skeptical analysts. However, There is agreement on one point. The signal is unusually clean. Natural radio emissions tend to drift in frequency, lose coherence, and vary in intensity. The emissions associated with 3I Atlas maintain stability over observation periods longer than expected. They do not fade rapidly. They do not fragment into noise. Instead, certain components remain locked in phase. This coherence is not evidence of artificial origin, but it is an anomaly in science. Anomalies are not conclusions. They are starting points. They indicate that existing models may be incomplete or that rare conditions are present. The correct response is not immediate reinterpretation, but deeper measurement. Another noteworthy aspect is how the signal's strength changes with distance. As 3I Atlas moves closer to the Sun and Earth, the radio emissions grow stronger. This scaling is consistent with a power source linked to solar energy. Solar radiation increases sharply with decreasing distance. Any system that harvests or responds to solar input would show this pattern. At the same time, many natural plasma processes also intensify closer to the Sun. The signal does not appear to be isotropic. It is not radiating equally in all directions. Instead, it shows directional dependence that varies with the object's orientation. This, again, does not prove intent. Directional emission can arise from geometry alone. Surfaces, cavities, and field alignments all influence how energy escapes a system. What remains clear is that the radio data cannot be dismissed as simple background noise, nor can it be confidently classified as artificial transmission. It occupies an ambiguous space where multiple explanations overlap. Each explanation requires assumptions, and none resolves all observed features without leaving residual questions. If the emissions are natural, they represent a rare combination of rotation, composition, magnetic interaction, and geometry. If they are artificial, they imply technology capable of long-term dormancy, self-activation, and complex signal generation after thousands of years of exposure to interstellar space. Both possibilities are extraordinary in different ways. At present, no claim can be supported beyond the data. There is no confirmed message. There is no decoded information. There is only a structured signal increasing in strength as solar energy increases, emerging from an object that has already defied expectations in its motion, surface behavior, and interaction with its environment. The wave itself carries no interpretation. It propagates through space according to physical law, indifferent to meaning. What it represents remains unresolved, but its existence marks a shift from passive observation to active listening, expanding the scope of inquiry beyond what light alone can reveal. As radio observations continue to accumulate, public discussion has expanded rapidly, but institutional responses remain grounded in a different set of priorities. While speculation focuses on meaning and origin, space agencies are preparing for the physical reality of a close interstellar flyby. For organizations like NASA and the European Space Agency, the primary questions are practical. They are concerned with trajectory certainty, environmental interaction, and time, the closest approach is imminent, and the window for high-quality observation is finite. Once 3I Atlas passes the Sun and begins accelerating outward, it will quickly fade from reach, carrying with it information that may not be recoverable for generations. From an operational standpoint, this moment is defined by constraints. Observation schedules are compressed. Instrument time is limited. Data streams must be prioritized. Agencies are not searching for communication or symbolic meaning. They are assessing potential hazards, validating orbital models, and ensuring that no unexpected interaction poses a risk to spacecraft or infrastructure. These assessments are routine whenever an object enters the inner solar system, regardless of origin. In this case, the object's interstellar nature adds complexity, but it does not change the methodology. Current orbital solutions indicate that the closest approach will occur at a distance of approximately 270 million kilometers. This is farther than the distance between Earth and the Sun. At this range, there is no risk of collision, no gravitational disturbance, and no physical threat. Plasma interactions and dust shedding remain localized to the object itself. From a safety perspective, the encounter is uneventful. From a scientific perspective, it is rare. As the object swings around the Sun, its velocity will increase, following well-established gravitational dynamics. After perihelion, it will exit the inner solar system on a hyperbolic trajectory, never to return. This asymmetry is what makes the present moment so valuable. There is no second pass. There is no opportunity to wait for better instruments or clearer models. The data collected now will define the encounter permanently. Official assessments released in recent briefings emphasize this point. Based on high-resolution imaging, dust behavior, and statistical modeling, agencies continue to classify 3I Atlas as a natural object. The absence of large-scale structural features, the consistency of dust release with sublimation under solar heating, and the plausibility of plasma-driven radio emissions all support this interpretation. From an institutional standpoint, natural explanations remain sufficient. They are not proven, but they are adequate within existing frameworks. This position reflects a broader principle in science. Extraordinary interpretations require extraordinary evidence. When multiple explanations remain viable, the least assumption-heavy model is preferred. This does not imply dismissal of anomalies. It reflects caution in assigning cause. Many past anomalies have resolved with improved data or refined theory. Agencies are aware of this history, and their public communication reflects it. At the same time, even the most conservative assessments acknowledge the object's age and provenance, whether natural or artificial. 3I Atlas predates human civilization by a wide margin. Its material has been exposed to interstellar radiation, extreme cold, and long-term isolation. It carries a chemical and physical record of conditions beyond the solar system. In that sense, it is not ordinary. It is a carrier of information, regardless of intent. This perspective is shared across a wide range of scientific commentary. While opinions differ on interpretation, there is broad agreement on scale. If the object were technological, it would originate from a time when Earth itself was geologically unstable, long before biology or intelligence emerged here. Any such technology would be ancient by human standards. If the object is natural, it is still a relic, preserving conditions from another stellar environment. In either case, its value lies not in what it might say, but in what it can tell us through measurement. The idea of the object as a messenger does not require agency. Information does not need intent to be meaningful. Isotopic ratios, molecular composition, surface morphology, and interaction with solar forces all encode history. When scientists study meteorites, they extract timelines of planetary formation. When they study comets, they infer early solar chemistry. An interstellar object extends that practice beyond the sun's influence. The encounter also highlights how the solar system functions as an open system. Matter does not remain confined. Objects enter and leave over cosmic timescales. Interstellar exchange is not hypothetical, it is ongoing. Though usually invisible, 3I Atlas is notable because it is detectable, not because it is unique. Its passage demonstrates that the boundary between stellar systems is permeable. One hypothesis that has drawn attention frames this exchange in biological terms. The so-called Gardner idea suggests that interstellar objects could distribute chemical building blocks across systems. This does not require intention. Natural processes already accomplish limited transfer through meteoroids and dust. An object shedding organic-rich material as it warms could contribute trace amounts of foreign chemistry to the solar environment. Such contributions would be dilute, but over geological timescales, accumulation matters. From this perspective, 3I Atlas passing through the inner solar system represents cross-pollination at a molecular level. Carbon-bearing dust, water, ice, and simple organics released into solar space mix with native material. This process does not target planets. It does not guarantee biological impact. It simply adds complexity to an already dynamic system. Whether this mechanism is natural or engineered remains an open question, but its physical plausibility is established. What is clear is that the solar system is not isolated. It interacts continuously with its galactic environment. Stars move through molecular clouds. Radiation fields overlap. Objects drift between gravitational wells. The idea of a closed, self-contained planetary neighborhood is an illusion created by short observational windows. When those windows widen, movement becomes apparent. The data collected over the past day have reinforced this view. The transformation of the coma, the anomalous tail geometry, the structured radio emissions, and the timing of these changes together alter how interstellar visitors are conceptualized. They are no longer treated solely as curiosities. They are treated as systems interacting across domains: mechanical, chemical, electromagnetic. Uncertainty remains central. No single observation resolves the object's nature. Each adds constraint. Together, they narrow possibilities without collapsing them to one answer. This is the normal state of frontier science. Progress occurs not through revelation, but through accumulation, as 3I Atlas approaches its closest point and then recedes, the opportunity for direct measurement will diminish rapidly. The radio signal may weaken, optical resolution will drop, plasma interactions will subside. What remains will be the dataset, fixed and finite. Analysis will continue for years, possibly decades, extracting new insights from archived measurements. The encounter does not deliver closure. It delivers context. It demonstrates that interstellar space is not empty, that objects can persist across immense spans of time, and that the solar system participates in a larger material network. Whether 3I Atlas is a product of chance physics or distant engineering, its passage expands the boundary of what is considered normal. The sky has not changed. The methods have. With modern instruments, coordinated globally and operating in real time, transient events become opportunities for collective measurement. 3I Atlas is one such event. It does not answer every question it raises. It reframes them. The lasting impact of this encounter will not be a declaration about origin, but a shift in how future interstellar objects are approached, measured, and understood.